These are the notes on solubility product constant, or the Ksp notes. It'll be helpful to have a calculator and a periodic table available while you complete these notes. So we've been talking about equilibrium in this unit, and we wrote equilibrium expressions. Now we're going to look at a specific type of equilibrium, which is solubility. So solubility is described as the state of equilibrium where the molecules exist between a solid state and aqueous ions in a solution. So we've talked about so far this year that something is soluble or insoluble, but really it is more complicated than that. And that process of if we have something that is solid and then dissolved in water, that is an equilibrium process. So we have that reversible reaction where those silver ions are going to break from the sulfur ions and are going to be free floating in that aqueous solution with those. And so this is that reversible reaction. And once this reaches equilibrium, we have silver ions that are going to be dissolved and floating freely in water, which would be kind of the maybe green ones over here. And then we also have those constantly in that dynamic equilibrium, maybe pairing up, two of these pairing up with a sulfur to be in that solid state. And so when something's dissolved, if it is slightly soluble or even technically insoluble, or even soluble, it means that it is going between being in that solid state and those free ions constantly. And so these green ions aren't always going to be free ions. At some point, they might pair up with a pink sulfur in order to form that solid, and another solid Ag2S is going to break up into those ions. And so that is an equilibrium state. And solubility isn't just it all dissolves or it doesn't dissolve. We actually have a couple ways to describe solubility. If something is soluble, that means that for every liter of water, more than 0.1 moles of the substance is going to dissolve into ions for that ionic compound. And that's what we've called as soluble so far. We've also actually referred to things that are only slightly soluble as soluble so far. Something is classified as slightly soluble if, for that 1 liter of water, 0.001 to 0.1 moles of that solid dissolves in that liter of water. And if something is insoluble or sparingly soluble, it doesn't mean it doesn't dissolve at all. It just means that such a low amount, less than 0.001 moles of that solid dissolves per liter of water. It doesn't mean that it actually never is going to break into ions. And so as we are looking at these, we are going to be kind of focusing on these slightly soluble salts because those ones have that equilibrium that is notable, where we are going to be looking at, well, what concentration of that is dissolved in that aqueous solution and what concentration of that is not dissolved with those. So that is what we are going to look at. You do not need to know these criteria, but you do need to understand that that solubility is an equilibrium process. And if something is dissolves, that doesn't mean that it all breaks up into ions. Some of it could stay solid based on these definitions. And so here these are, we actually use an equilibrium constant to describe how soluble something is. Instead of saying the concentration per liter of water to classify, which is molar solubility, it's actually more common to use a equilibrium solubility constant, a Ksp, so SP, solubility product constant. And so here's a selection of those. If we look at these different compounds, barium fluoride is, and we describe its solubility based on that, so 2.45 times 10 to the negative 5. You'll notice we have some that are even smaller. We have a 10 to the negative 13. And so these are just K values, K equilibrium values, like we did in our last set of notes, but that SP means it's specific to a solubility reaction. All right, And you are never going to need to memorize a Ksp value. You need to know what a large or a small Ksp value means, which we'll talk about in a little bit in the notes. And you'll need to do calculations with those, but you will be provided what that Ksp value is. And so how do we write these solubility reactions? Well, dissolving a solid ionic compound in water results in those ions disassociating. And then this is the reaction that's used to write that equilibrium expression. So because we are looking at these equilibrium expressions, these are reversible reactions because, again, we're going between our forward and reverse reaction. And so as we look at, write the reaction of the following ionic solids dissolving in water, well, calcium, if we look at our periodic table, has a +2 charge. Fluorine, fluoride, is a -2. So when I do my drop and swap, I get CaF2, and that is a solid. So we have a solid ionic compound, and then we're going to have that reversible reaction. You're going to use that double-sided arrow, whatever your preferred way to write that is. And how would calcium fluoride dissolve? Well, it's going to break into ions. It's going to break into calcium +2 ions, because that's the charge on calcium. And those are going to be aqueous, floating in that water, or dissolved in that water. And then we have fluorine, which is a -1 charge. And because this is an ion, this is not diatomic. It's not F2. It's the fluorine -1. And that is also aqueous. We do, though, have to balance this. We would have 2 fluorines. And so because we have 2 in our ionic compound, when this breaks up, we would have 1 + 2 and 2 -1 ions. And so this is my balanced solubility reaction for the dissolution or the dissolving of calcium fluoride. If you want, try the next one on your own. Iron 3 sulfide. Here is iron. It's a transition metal, so this is telling us it's a +3. Sulfide is sulfur. That's a -2. And you could have polyatomics. We have some in our examples later. And then when we do that drop and swap, well, Fe2, we need 2 irons, and S3, 3 sulfurs. And again, that is that solid that is going to dissolve into ions. And so what are our ions? Well, we have Fe. Iron has a +3 charge when it dissolves, and that is aqueous, plus, and then we're going to have our sulfur is going to have a -2 charge when it dissolves, because that's it wants to gain those 2 electrons to get that full octet. And so we use whatever those charges are that we used for our drop and swap. Those are the charges our ions get. And now I just need to make sure that this is balanced. Well, I have Fe2. I need a 2 then in front of that Fe. And then S3, I need a 3 in front here. So I always have to have, so Fe2, I need 2 irons. S3, I need 3 sulfurs. The fact that these are ions, that means 2 times +3. Well, that's a +6 charge. That's going to balance out the -6 charge that we get from our 3 sulfurs. So these are our dissolution reactions, or that solubility reaction. And this is actually going to be our first step as we then start to write our Ksp expressions. So with those equilibrium expressions, we're using the same rules that we have when we learned how to write our KEQ expressions. It's just Ksp is specific for if we're looking at solubility. So that solubility product constant. Again, our K value doesn't have units. And so we need to first write that balanced reaction of our solid ionic compound dissolving in water. That's our dissolution equation. We just practiced that. You always are going to have a neutral solid ionic compound as your reactants. Your products are always going to be those aqueous ions. And then you need to balance. Ions never get subscripts. It doesn't matter if it's diatomic. It's not neutral, so it gets whatever the charge is. And then we write our equilibrium expression. And remember, we don't include solids in an equilibrium expression because solids don't have a changing concentration. And with equilibrium, we're looking at how gases and aqueous solutions are changing concentration in that equilibrium process. And so when we're writing our equilibrium expression, it's, remember, for our KEQs, it's always products over reactants. So it's going to be the same thing here. Our KSP is going to be our products. Well, our products are our ions. And so we'll have the concentration of our ions on the top over, well, we don't include solids. And so we're always going to have a 1 down here for that KSP. Because those reactants are solid, the concentration doesn't change, and so we always put a 1. And that's always going to be the case for when we're looking at KSPs. We won't have that, anything in that denominator. A reminder, coefficients from your reaction become exponents. So if we end up with coefficients, a coefficient on A for balancing, that's going to become an exponent. Same thing if you had a coefficient on B, that's going to become an exponent on that concentration. So same rules as writing our KEQ expressions. And then what does this KSP tell us? Well, if our KSP is greater than 1, that means that we have a higher number or larger number in the numerator, meaning that our products are favored. And so that means that more salt has dissolved into ions because we have those favored products. If our KSP is less than 1, that means that our denominator is going to have the larger value, which means our reactants are favored. Well, that means that we're going to have more of our salt intact as a solid ionic compound. That is a reactant favored with that. And that would be something that is not, that would be like sparingly soluble, whereas something with a KSP of greater than 1 would be something that is very soluble. So let's look at modeling these KSP values based on that constant. And then we will go into some calculations. So again, what does that KSP tell us? It's telling us how much of that ionic compound is going to dissolve. And so with our KSP greater than 1, more of it has dissolved. KSP less than 1, more of it's intact. And it comes back to us writing that those KEQ, any of our K values, are concentration of products over concentration of reactants. For our solubility, our reactant is always the solid. The product is always our ions. And so if you can kind of think of it that way. And so in the 2 beakers below, show a side-by-side comparison that represents how differently potassium chloride and lead 2 chloride dissolve based on their KSP values. So if we have potassium chloride, that has a KSP value of 21.7. That means if this is a KSP value that is greater than 1, that means more has dissolved. So our number on the top is greater. We are going to have more ions than we have solid. And so with that, well, how is that KCl going to dissolve? It's going to dissolve into a K plus 1 and a Cl minus 1. And we are still, though, going to have a little bit of that KCl solid left. But we are going to show that most of that dissolves. It's going to take up more space in our beaker. But we do have a small portion of that solid that remains that solid that's not going to break into ions. As we're looking at that PbCl2, well, this KSP value is less than 1. Anything with a negative exponent is going to be less than 1, which means that more of that is intact as a solid. That's less than 1. That means the number on the top is smaller than the 1 for our solid on the bottom. And so that solid is going to be favored. And so as we're looking at this, I've got that PbCl2 solid, and that's going to take up more space in my beaker. But I am still going to have some that dissolves. And how's that going to dissolve? Well, we're going to have a lead plus 2 ion, but we're also going to have 2 chlorine minus 1 ions because we need to have that balanced. 1 lead, 2 chlorines, but now it is dissolved into ions. So even if we have something with a really low KSP value, it still means that a small amount dissolves. It doesn't mean none of it dissolves, but it means that most stays in that ionic compound solid. All right, so let's go on to how can we use this. So if we have our K value for that equilibrium constant, how can we find what concentration of ions we have? So what is my concentration of potassium or chlorine ions, or my lead ions or chlorine ions in these? That's going to be our goal, to find those concentrations. And we're going to do this for slightly soluble salts. That is when this is most helpful. For doing that, we might, I think we have one example, or we usually do this when we have those slightly soluble salts. So we're going to see those negative exponents just because it is not helpful necessarily when we have something that is soluble or classified as soluble. So we do this mostly for those slightly soluble salts with those really small Ksp values. And so those steps, we're first going to write that dissolution equation, specifying states of matter, and we are going to balance that reversible reaction, just like we practiced in the two examples earlier. We're going to then write the Ksp expression, which is just like writing a Keq expression, but it's specific to solubility or dissolution equations. And then we're going to need to solve for the molar solubility. So what is that X value? And molar solubility was discussed up here. So how many moles per liter of water are dissolving? And we need to do that because if we have something with 2 moles versus 1 mole, then we need to make sure we take into account those difference in moles. So we find this molar solubility, and then our last step is going to be, well, what is the concentration of the specific ions for that? And so we're going to go through this process. I'm not going to read through all of it right now, but I'll reference it in our first problem of how we can go about and do this. One thing to note, in AP chemistry and in higher level chemistry courses, you're going to use an ICE table to solve equilibrium problems. The approach we're taking is a simplified method for when we're working with K values that are really small with that. And so there are other ways to solve this that works for any sort of problem. The approach we're going to take kind of simplifies down what we're going to do for these specific slightly soluble salts that we're going to focus on. All right, and I'll talk about these steps as we get to those. So let's start by writing the dissolution equation and writing the Ksp expression for this first example. We have aluminum hydroxide dissolves, and with this, we are also provided the Ksp value down here. So dissolving, we're going to write that solubility equation. We've got our aluminum, which is a +3 charge. Hydroxide is a -1. We need to make sure we are using our periodic table, doing that drop and swap. And so we're going to have in our equation, aluminum is going to get, we're going to have 1 aluminum, but then we're going to have OH hydroxide. We're going to have 3 of those, and that's our solid. So we always are going to have a solid on the left, and then we have our double-sided arrow because this is a reversible reaction. And we're going to look at those ions. And so that's going to break into aluminum ions, which have a +3 charge. Those are aqueous. And we're going to have hydroxide ions, which have a -1 charge. And those are aqueous. Your polyatomics can stay together, just like we've been looking at when we're looking at breaking these up into ions earlier in the year, when we were looking into the fact that solubility means a lot of different things. And then I look at this and I want to balance it. So I have 1 aluminum on both sides. I have 3 OHs on this side, so I need a 3 here. And that's going to be also to get us, so we have that neutral +3, and then 3 times -1 -3. So that was our first step. Let's writing our balanced equation. Now let's write our Ksp expression. And remember, for any of our Keq expressions, and this is just specific Ksp because we're doing, or we're dissolving, we're looking at that solubility product. This is concentration of products over concentration of reactants. And those square brackets mean concentration, so we only include the things that can have varied concentration, which are aqueous and gas. So we don't include solids, but we do include anything that's aqueous. And so with our solubility, it's always just going to be the ions that we get when those break up. So Ksp is going to equal, well, I have aluminum ions, so Al plus 3. So I'm going to have the concentration of my aluminum ions. And then I have my OH minus 1 ions. And when we're looking at this, we have 3 OHs. Those coefficients become exponents in our Ksp expression. And that this is over, well, we're not including anything in the denominator because this is a solid. And so this is over 1, but we don't necessarily have to write that over 1. You're welcome to write the over 1 if you would like. All right, so as we look at this now, what's our next step? Because we are going to actually find the concentration of each ion. We're going to find what is the concentration of aluminum, what is the concentration of hydroxide ions. And that brings us to step 3. We are going to solve for molar solubility, which is, we're going to use X to represent that by substituting the following into our Ksp expression. So we have our provided Ksp value. So as I look at this expression I wrote, I have the value for Ksp. Ksp is equal to that 1.9 times 10 to the negative 3. And so I'm going to take this expression and I'm going to plug that in. And I always plug it in on the left because we write Ksp first. So we have that the Ksp value for this is 1.9 times 10 to the negative 33. And then I need to look at how do I solve an equation if I have 2 variables? Well, I need to look at the fact that I have a ratio of 1 aluminum to 3 hydroxides, and those concentrations have to be the same because they all need to be paired up in that solid. And so what we do is we use a common variable because we have that 1 to 2 ratio, or 1 to 3 ratio, but that ratio is based on a common concentration. And so what we're going to do is we look at, okay, aluminum, I have 1 aluminum, so I'm going to plug in 1x for aluminum. I have 3 hydroxides, so I'm going to plug in 3x for my hydroxide. So I have that common variable of x, but I do need to remember that I have that to the exponent of 3 because I have 3 OHs. I do need to cube that concentration. And so our molar solubility is X. That's telling us how much is soluble per mole. We have 1 mole of aluminum, so we just have 1x. We have 3 moles of hydroxide, so we have 3x, and then that keeps its cubed. And now I have an equation that only has 1 variable x, and I can use my algebra to solve. And so I did both of these parts, put that common variable in on the other side with my Ksp value on the left. Now let's solve that algebraically for x, which is our molar solubility concentration. So looking at this, I'm going to simplify the right side first. I need to cube that 3 and I need to cube that x. So I'm going to have x times, well, 3 cubed is 27 times x cubed. As I'm simplifying it, I'm going to bring that 27 out front. If I have x to the first times x cubed, I add those exponents to get x to the 4th. And that equals our 1.9 times 10 to the negative 33. I'm just going to carry that down. And now this is something that I can solve algebraically. I need to get x by itself. The 27 is farther away, so I need to divide both sides by 27. And once I divide by 27, now I have this 1.9 times 10 to the negative 33 divided by 27. That equals x to the 4th. Well, how do I undo an x to the 4th exponent to get that x by itself? Well, we need to do, just like if we had x squared, we would take the square root. we need to now do the fourth root of both sides to find what x is. And we're doing the fourth root of this whole expression. I just go ahead and solve all of that at one time instead of having to write those out. But if you wanted to, you can do this division and then do the fourth root on that number. And then we get x equals, on your calculator, if you're using one of the calculators I have in class, you're going to press the 4 button, and then you're going to press the, you're going to go that, you're going to do the second button, and then the x squared, nope, the exponent button has that x to the, sorry, it has the x root above it. And that by doing the second, that's how you'll get that x root. So you go 4, second, and then the caret button to get the x root. The 4, whatever you put in front is what you're telling it to take that root of. And then we would type all that in after that, making sure to close our parentheses. So once I type that in and I solve, I get 2.9. I'm going to keep 2 sig figs from that 1.9 that I had. So 2.9 times 10 to the negative 9th, you're going to get scientific notation numbers. So make sure you're looking at the end of your value on your calculator. So times 10 to the 9th, because we have really low concentrations when these are sparingly soluble. And so that x value is our molar solubility. So for every mole, that's how much is going to dissolve. So now if we look at our aluminum plus 3, well, I only have 1 aluminum. So to find the concentration of each ion, well, I only had 1 x for aluminum. And so that aluminum plus 3 concentration, again, square brackets means concentration. Well, that's just 1x. So that would just be 2.9 times 10 to the negative 9th molar. That's how many ions will dissolve per liter of water. If we look at our hydroxide, well, our hydroxide was balanced with a 3. We had a 3x. So that means that as we go through, we need to then put in 3x. So we're going to do 3 times 2.9 times 10 to the negative 9th to get that molar, that concentration of that ion. And I got 8.7 times 10 to the negative 9th molar. That's the concentration of those OH ions, because we have 3 OHs to every 1 aluminum. All right, so it is a lot of work, but with that solving of our equation, but the process stays the same. If we look at how can we model this, well, our Ksp value is less than 1. So that means our Ksp value is less than 1. That means that the number on the top is smaller. And so we're going to have more of our reactants. This is slightly soluble. And so for all of these, we should expect that we only have a little bit of dissolved ions, or a small amount, and then we have a lot more of that aluminum hydroxide solid, like that. So slightly soluble, meaning only a little bit is going to dissolve. Most of that is going to be in that solid form. All right, let's go ahead and do another one together. If you want, feel free to pause the video and try on your own. We're going to follow that same process. We're going to write the equation, and then we are going to write the expression and solve for that molar solubility. So we've got silver 1 chloride. So silver is a +1, chlorine's a -1. Writing my equation, AgCl, that's a solid. We need to make sure we're including states of matter because that tells us what to include in our Ksp expression. And then that is going to dissolve into silver, aqueous silver +1 ions, and aqueous chlorine -1 ions. This one, we already have just +1, -1. There's one of each, and so we don't need any coefficients on to balance. writing our KSP expression, that KSP, remember it's products over reactants. For our solubility, we're always going to just have our ions. So we have our silver +1 ions and our chlorine -1 ions. We have the concentration of each of those multiplied all over 1 because a solid is not going to change concentration, so we don't include that. So if you want, you can put the over 1, or we can leave it blank. So now let's solve for molar solubility. Well, I know that KSP equals silver +1 times that chlorine -1 concentration. We also know that our KSP value is 1.77 times 10 to the -10 because that was given to us. So we're always going to be provided those KSP values. And then we need to have a common variable. We need to get an equation with one variable. Well, these are always going to have a 1-to-1 ratio. So let's make that ratio into a variable that we can easily solve with. So we have 1 silver and 1 chlorine. So we're going to have 1x times 1x. In our last one, we had a 1-to-3 ratio. Now we have a 1-to-1 ratio, so we don't have anything other than x's, which makes this one a little easier to solve. We can go 1.77 times 10 to the -10th equals, well, x times x is x squared. And to solve for x, I can take the square root of both sides. I don't have to do any other dividing to get x by itself. That square root cancels the square, and I can plug that into my calculator. On your calculator, if you're using one of the ones I have, to get that square root, you're going to use the second button, and then you use the x squared button. Above that, in that light blue, it has the square root function, and then you type your number after it. And these problems are good ones to use your E button with your scientific notation, that double E, so that your number doesn't break apart. All right, putting that in my calculator, I get x is 1.3, oops, not yet, sorry, I changed something. Square root of 1.77. Oh yeah, 1.3, I'm gonna just do 3 sig figs here, so 1.33, and that one is times 10 to the -5th. And that is the molar solubility. So each mole is going to have that much dissolved. So what is the concentration of each ion? Well, we have 2 ions. We have, what's our concentration of silver ions? Again, we do those square brackets to say we're showing concentration. Well, we only have 1 silver ion, and so that's just going to be equal to x. It's just going to be 1.33 times 10 to the -5th molar. These are concentrations, so we need that molarity unit on there. And then our chlorine -1 is also, we just have 1 chlorine, and so that's going to have that same 1.33 times 10 to the -5th molar as the concentration of each ion. So these were both balanced with a 1, and so these are both going to just equal that x value. What is that going to look like in terms of our, if we were to model that? Well, these are slightly soluble salts. That's a really low KSP value, less than 1. So we're going to have only a few dissolved ions. Most is going to be left as a solid. All right, if you feel confident in these, the answers for the next 2 are on the last page of your notes. Otherwise, I'm going to go through one more, and then I'll show the work for the last one after I work through the next problem. All right, we've got calcium phosphate. This one has a polyatomic. It doesn't change anything about what we're doing. We still have a +2 and a -3. So I'm going to have my Ca3 PO4 2 solid when that dissolves into ions. I'm going to have calcium. Calcium has a +2 charge. Again, whatever charge we're using when we are writing our ionic compounds, that's the charge we're going to see with our ion, because that's the ion calcium would form. And that's going to be aqueous, plus we've got that phosphate, PO4 -3, aqueous, and we need to balance. So we've got 3 calciums here, so we need a 3 here. We've got 2 phosphates here, so we need a 2 here. So there is my balanced dissolution reaction. And now I can write my Ksp expression. Ksp is the same as Ke3, products over reactants. My products are on the right. Those are aqueous, so I include those. I'm going to have concentration of calcium +2, but I have 3 of those. So again, in this step, our coefficients become exponents. And I have my PO4 -3 ions, but I have 2 of those in my balanced reaction. So again, my coefficient becomes an exponent. So these are my products over reactants. Well, our reactant is a solid, and so that would just be a 1 in the denominator. Now that I have that expression to solve for molar solubility, I need to plug those in. I need to plug in my Ksp value. I'm going to plug that in on the left. So I'm going to have 1.3 times 10 to the -26. That's going to equal, well, I need to get a equation with just one variable. So let's use x to show the molar solubility. But I have calcium +2, I have 3 calcium +2s, so I'm going to have a 3x. I still, though, have that exponent of 3, so I'm going to have that 3x cubed. Then I'm going to have my PO4. I have 2 PO4s, so we're going to have 2x for our 2 PO4s, our 2 moles of phosphate ions. But I also, again, still have that 2, so I need that 2 here. So I did my substitutions, taking into account how many moles I have and getting a common variable. Now I can go through and simplify to solve for x. So I've got 3x all cubed. That means we're going to have 3 cubed, which is 27, times x cubed. We have to cube everything in those parentheses, times 2x squared. So that is 2 squared, which is 4 times x squared. Simplifying on the left to get all of those numerical values together and my x's together, I'm going to have that 27 times 4, which is 108, and then I have x cubed times x squared. Well, x cubed times x squared, if we add those together, the exponents, we get x to the 5th. So 108 x to the 5th is going to equal that 1.3 times 10 to the -26. So we have an equation with just one variable. My goal is to get x by itself. That 108 is multiplication is a weaker operation than an exponent. So we are going to divide both sides by 108. So that 108 cancels, leaving us just that x to the 5th. That x to the 5th is going to equal that 1.3 times 10 to the -26. And so how do we get x by itself? Well, we are going to need to take the 5th root. So because that's an x to the 5th, we're taking the 5th root of both sides. Again, on the calculator, you're going to put a 5, second, and then the caret button has the x root above it. And then we're going to type in these numbers. We need to make sure that scientific notation, make sure you're using your E button or putting parentheses up here. And that gives us x by itself. And so then x is 2.6 I'm going to do 2 sig figs because that 1.3, 2.6 times 10 to the negative 6 molar. And that's the molar solubility, the solubility for each mole that we have. So as we are going to find, well, what is the concentration of each ion? We now need to go back and look at, well, how many ions do I have? So my calcium plus 3 ions, nope, calcium plus 2. Well, I have 3 ions. I had that 3x from above. So I'm going to go 3 times that 2.6 times 10 to the negative 6, which is going to give me 7.8 times 10 to the negative 6 molar. That's the concentration of the calcium ions. For my phosphate ions, PO4 minus 3, well, that was balanced with a 2, so that's going to be 2x. So 2 times that 2.6 times 10 to the negative 6 is going to give us 5.2 times 10 to the negative 6 molar. So those are the concentrations of each of our ions from that, or in that, if we are looking at that dissolving. All right. Here are the answers to this next problem. Feel free to pause the video, take a look at that. I did forget to model this one. You should be able to model that one. It's similar to what we did before, but making sure that we have that 3-to-2 ratio. So we'll have 3 calcium plus 2s, 2 PO4 minus 3s, and then that calcium phosphate solid, oops, in the bottom. And our ions are going to be very small because that's only slightly soluble. All right, here's this next one. Your products are your ions. Your reactants are going to be your solid. So take a look at that, and the answers are here for you at the end as well. Reach out to your teacher with any questions.